Anasuya Aruliah obtained her physics degree from Somerville College, Oxford in 1984 and undertook a PhD at University College London, graduated in 1991, where she continued as a postdoc in the atmospheric physics laboratory. She's been running the group's grad-based optical program since 1995 and will be talking to us today about their work on estimating the top of the thermosphere and the consequences for our space-based infrastructure. So whenever you're ready, please take it away.
Okay, thank you very much for the introduction. So my question is, where is the top of the Earth's atmosphere? It's not a subject that's actually been worried about until recently, and I'd like to try and show you why it's important to make this decision at a very critical time in terms of industry and research. So I have a number of colleagues who have been collaborating in this. In particular, it's been a collaboration between my group, the Atmospheric Physics Lab at UCL, and between the Space and Geodesy and Navigation group in the Faculty of Engineering at UCL, who do precise orbit determinations. And we've also had Ingrid Knossen come on board to help us investigate this issue. And she is a modeler. And we have had several MSc and MSci project students whom we've been very grateful for doing a lot of the investigations in detailed investigations to help us in our directions with combining atmospheric physics with precise orbit determination. So here's a graph from McDowell from 2020 showing all the different levels of the atmospheres, which are defined by the temperature gradients. So tropospheric temperature drops with altitude, stratosphere increases, mesosphere drops, thermosphere increases until it becomes an isotherm. And then the top of the atmosphere is the thermosphere, and then we have the exosphere above that. Now, the issue is, where is the top of the thermosphere? Because from the thermosphere downwards, we're dealing with a fluid atmosphere. And when we have a fluid atmosphere, we can use the Navier-Stokes equation, which is an acceleration per unit mass equation, which then has the different forces in order of magnitude. So the largest force on the gas is gravity, followed by pressure gradients, Coriolis force, ion neutral collisions, viscosity for the thermosphere. Now, above the thermosphere, we have the exosphere. And here the particle collisions are so rarefied that the particles move in ballistic orbit and are only controlled by gravity. Now, the global circulation models we deal with are physics-based models, which are solved numerically, and they presume that we're dealing with a fluid. And so the equations that are used are the conservation of mass for the chemistry and dynamics, conservation of linear and angular momentum, and the conservation of energy. And the numerical weather prediction models include complex equations representing physics and chemistry, data assimilation, and parameterization of subgrid scale processes, because with finite computing resources, we're not able to model things within a few hundred kilometers horizontally for the thermosphere. When you get down to weather, tropospheric scale sizes, you can go down to, say, 50 meters for weather forecasting, but we don't have the data or the computing resources to justify the very high resolutions that tropospheric weather can use. And we have, with the numerical weather prediction, they now use data assimilation, and they use ensemble forecasting to give probabilistic forecasts, which all come from the weather community. So with the context, we have to remember that there is an exponential decrease in particle density with altitude. You have to remember that the thermosphere is a fluid, which means that the particle density is high enough for collisions, which means that there is a bulk response of the flow of the gas and the heating of the gas. Meanwhile, the exospheric density is so low that particles move without collisions and are therefore moving in ballistic Galilean trajectories under gravity. And so the mean free path is much larger than the scale height. So it is actually very difficult to combine thermospheric and exospheric modeling. There is an overlap between them because it depends on what particles you're dealing with. So it is a very complex subject, and exospheric study has a fewer people studying it than in the thermosphere ionosphere community. So the question that I'd like to pose is it justified to extend thermospheric fluid models into the exospheric height regions for satellite orbit prediction? Because the only reason for extending our models has been because of the serious need to predict satellite orbits very accurately. So the question here, one of the reasons here is in February 2022, the Starlink mega constellation lost 38 out of 49 satellites that were launched. And they used the empirical model, the NRL MSIS E00, which predicted that there was going to be a minor storm during this launch and that the density enhancements would only be about 20%. And so it was safe to launch. But in reality, there was a KP5 conditions lasting 6 hours. And when there was a post-storm analysis, a physics model called WAM-IPE modeled 50 to 100% enhancement of thermospheric densities. And so we had the majority of these satellites were brought down by atmospheric drag. So the trickiest physical conditions to predict are moderate to extreme geomagnetic conditions. We have another issue in that climate change and increasing carbon dioxide is causing a cooling and contraction of the thermosphere. And this means we have longer lifetimes for satellites and space debris. Now, the expansion of the atmosphere acts like a Hoover cleaner, so that whenever the atmosphere is heated and expands into the paths of satellites, when it cools down, it drags down these satellites. Well, the satellites, the increased atmospheric drag drags down satellites. So we get a clear out of dead satellites and space debris whenever we have geomagnetic storms and when we have solar maximum conditions. But when we have a cooling atmosphere, we're losing that capacity. The current solar cycle is radically different from the previous solar cycle. And so we have been experiencing the largest geomagnetic storms in over 20 years since the Halloween storm in 2003. And some of us may have been lucky enough to see aurora even down to the south of England. So here is a plot by Elko Doornbos in his 2011 thesis that many people have used because that's such an excellent plot, which shows on the left-hand side the height variations of temperature. And you can see that below the thermosphere, there is practically no change in the temperatures between solar maximum, solar minimum, or night or day. But there are very serious changes in the thermosphere, which is because it is so rarefied. And on the right-hand side, we have the density plot, which shows the exponentially decreasing densities. And it indicates the type of satellites and roughly where the satellites are, which are in the lower thermosphere region. So generally between about 400 to 600 kilometers altitude. Now, this is a slide from Ingrid, which is showing how there is a long-term trend where she ran the WACM-X model and showed the height of the top layer of the WACM-X model from the 1960s and predicted where it would go to beyond 2060, and showed that the carbon dioxide increase, the climate change that we're experiencing, she predicts a reduction of minus 3.4 kilometers per decade. So this is the top layer of the WACM-X model, and it's changing according to the solar cycle. Now here we have a way of looking, a schematic of looking at how models, the coverage that models have with respect to height. So we have these are the American models, and we have equivalent UK models and European models. So we have the no gaps USA model that goes up to 90 kilometers, which is the mesopause. And then we have the TIGE GCM model, which is the thermosphere, ionosphere electrodynamics global circulation model that goes up to 500 kilometers altitude in solar minimum and 700 kilometers in solar maximum. But very recently, an extra 4 pressure levels have been added to the top of the TIE GCM to reach up to 1,200 kilometers. And it has recently been released to the community. And the reason for going up to the 1,200 kilometers is largely because of the OneWeb constellation of satellites at 1,200 kilometers. So these are 650 satellites for business-to-business broadband internet services. And there is going to be a huge number of satellites which are going to fill the low Earth orbit region, because it's a very lucrative region to be working in. So we should be looking at the Knudsen number, which is the definition of a fluid, because the global circulation models only apply to fluid behavior. And the Knudsen number is given by lambda over L, where lambda is the mean free path of the particles, and L is a representative scale size of whatever whatever object is going through this fluid, to see is the behavior of the particles around this object behaving like a fluid or ballistically. So can we use fluid equations to predict the motion of this object? And so the Knudsen number shows that if you have a value that's less than 0.01, we have a continuum flow. So there are enough collisions to treat the environment as a fluid. But if the Knudsen number is greater than 10, we have free particle flow. And then we have to use Monte Carlo simulations to work out what are the pressure forces from all these particles hitting your object. So I will just show you that some of the reasons why we need to know the fluid behavior and how to predict for precise orbits. So this is an example of the re-entry of the Tiangong-1 Chinese space station on the 2nd of April 2018, and how difficult it is to try and predict where it's going to land with our existing models, atmospheric models. Here's another reason why we need to understand our atmosphere clearly, which is from the Extreme Space Weather Impacts on Engineered Systems and Infrastructure report by Paul Cannon, which is showing how we have the solar activity, how long it takes for all the different aspects of solar activity come to and reach the Earth. And at the edge, you see all the different communications and power grids and aircraft radiation and satellites and all the effects that affect us as a modern technological society. So we need very much to understand the whole of the sun to earth system for our modern society. And this is the dangers of an unregulated space industry. And we're now in the time of the Kessler syndrome, where this plot on the left is showing from 1957, when the Sputnik was launched, to modern days, when we have had this uncontrolled increase in the number of satellites and objects launched into Earth. And the problem is that through all of these satellites, the space has become so crowded, it will be too dangerous for us to be able to launch any future satellites, especially satellites carrying humans, in a safe manner. The bottom right shows a pizza box volume that was used, that gives an indication of the volume of safety that's required for a satellite to move, where if there is anything that encroaches into that safe area, then there is an alert and the satellite has to make movements to try and move up or down to escape collisions. Now, if we are going to have more satellites, we need to have more precise orbits, which means that the size of this pizza box can get smaller and we can pack more satellites in. Now, let's look at the ionosphere, thermosphere, magnetosphere system. So this is a slide from Jeff Forbes, which shows how very complicated the system is. And this is behind the whole atmosphere models, which assume a fluid behavior. And these are examples of equations that go into the Navier-Stokes equation, which is a horizontal momentum of a fluid equation. And so we need to know densities, we need to know winds, we need to know temperatures, we need to know then also with the ionosphere, we need to know ion neutral collision frequencies. So these are just some of the equations that we need. And from the equations, you see what are the measurements that we need to be making. So where is the top of the Earth's atmosphere? Is there a top, and how is it defined? And what happens to the thermopause, which is the top of the thermosphere, during a geomagnetic storm? So here's an example from a paper by Sutton et al. In 2006, where they've looked at the response of the thermospheric density to a severe solar event. So we have this X17.4 event where the AP was greater than 400. So the geomagnetic activity was extremely strong, but it happened extremely suddenly as well. And so the left column shows the response of GRACE, where the drag on the GRACE, because both of these had very precise accelerometers on them. So the drag on GRACE was converted into thermospheric densities. And the black line here shows the X-rays and EUV from the GOES 12 and the C instrument on the time satellites. And as you can see, that as soon as we have that flare, we have this very quick response in the density. The density increases at 490 kilometers for GRACE and at 400 kilometers for CHAMP. And the peak response time of the thermospheric density increase was 72 minutes, plus or minus 47 minutes on average. And the recovery time was 12 hours. So there is a rapid response and then a slow recovery of the thermospheric density. So how do we look at this schematically? So what we see here is storm phases as identified by the DST index. So we have the initial phase where the DST index increases, and then it drops into the main phase and becomes very negative. And then we have the recovery phase. So DST index is an index of the magnetometer perturbations. And this is over a period of days. So if we look at the equivalent, we have the quiet pre-storm. So this is just a schematic where we have the top of the thermosphere at about 400 kilometers. We have the initial phase as the Joule heating begins because you have increased particle precipitation, increased conductivity, increased electrical ionospheric currents in the thermosphere, which heat the thermosphere. So a sudden storm commencement begins. We get a heating of the atmosphere in the initial phase, continues to heat during the main phase, and then slowly the atmosphere recovers as the molecular components start radiating heat into space again. And then we have our hypothetical satellite 1, 2, 3, at different altitudes coming along. And all three of these are hypothetically outside the thermosphere, so outside atmospheric drag. But as time passes, so satellite 1 comes straight into the thermosphere, which has expanded into its path as happened with satellite 2, while satellite 3 can continue unperturbed because it is still outside the thermosphere. So we have an imperative to have complementary and independent observations alongside modeling. We cannot rely on modeling alone because models can do anything we want them to do. And we need observations to define the parameters and limits of the models. So we need to constrain models with observations, but we can't also rely on single instruments and single observations. We need that independent observations. We need to put that jigsaw together through many different observations. An example I'll give is one of the equations that for the ion neutral coupling is the parallel plasma velocities along the magnetic field lines observed by the iSCAT radar, and here neutral winds observed by Doppler shifts by Fabry-Perot interferometers, and a model and observation gives us the ambipolar diffusion equation. And by looking at these complementary measurements, we can see that the red line are the plasma field-aligned plasma velocities, and the blue line are the neutral wind velocities. So they're totally independent measurements, but they are co-located and they are complementary, and they confirm what we're expecting from fluid behavior. Here's a Joule heating equation showing all the parameters that go into it. So the ion neutral reduced mass, mean ion neutral collision frequency, neutral number density, and the difference between the neutral velocities and ion velocities, which we can measure independently using SuperDAM and Scandi plasma drifts and winds, respectively. And here's an example of the neutral wind modulation of Joule heating observed with Scandi and SuperDAM. So on the left-hand side, we have the green vector arrows give us the wind speeds and neutral wind speeds by the Scandi all-sky Fabry-Perot interferometer. And we can see with an all-sky photometer, we can see the red line intensities, which is an indication of the particle precipitation. So we can see how you have the aurora forming from about 7:30. You can see it a bit earlier than that. So you have a bright auroral arc at 7:45. And on the right-hand panels, we can see the calculation of the integrated Joule heating. And we can compare the two together to see what's happening. But the key thing that was found by applying the Joule heating equation is that we have to remember that when you have the solar wind magnetosphere electromagnetic energy, which is also known as the Poynting flux, that energy does not just go into Joule heating. It also goes into accelerating the neutral gas. And so if you look at the UN minus UI, so that is the difference between the speed of the neutrals and the plasma, if that difference changes, or if the ion neutral collision frequency changes because we have more, we have particle precipitation, which increases electron densities, then these factors will change what is the conductivity and what is the relative speed of these parameters in the Joule heating equation, which then modulates how much energy we have. that goes into Joule heating and how much energy is allocated to accelerate the neutral gas. And what this experiment showed was that the neutral wind response to ion drag before the aurora, so low conductivity, took more than 1 hour, but after aurora, it took only 8 minutes. And so it reduces the Joule heating because the neutrals quickly catch up with the plasma velocities. So this term becomes small, even though the conductivities have become large. And so there's less energy that goes into Joule heating, more energy has gone into acceleration. So this is where we need independent and complementary observations in our calculations and our interpretations of what's happening. So this is just to show you the location of the Fabry-Perots, and we have had a whole load more of scanning Doppler images from America. 3 new scanning Doppler images have been brought here. The Japanese have a Fabry-Perot they've moved from Tromsø to Skibotn, and so there's a whole load of extra instruments that were brought in purely for IceCat 3D. And Southampton has also a high time resolution imager that is brought called Embla to Skibotn. It's already had one called Ask at Longyearbyen, which has, and we are actually working on looking at low thermosphere, upper thermosphere comparisons of temperatures, which is all part of the energy calculations. And this is an example of Scandi, the wind speeds, that as the Earth rotates, then Scandi shows the different behaviors of the neutral winds within the region of the auroral oval and the Jungi cycle plasma convection. And here's another example of when you get heating, you get upwelling. So these are the neutral winds from the Fabry-Perot. You get upwelling, where you get heating, upwelling. And then when you're outside the heating region, you get downwelling because you have a convection convection motion. So directly where the heating is, you get upwelling, and then the atmosphere has to drop down outside the heating region to conserve mass and momentum. Now here we have the importance of cross-calibration of models with satellite drag measurements. Now here is a paper by Sean Brinsbra in 2015, where he compares the satellite drag converted into densities using the drag equation as given here. And he looks at the ratio of the satellite densities for several satellites, and he compares them with the DTM 2013 empirical model densities. And so this is the ratios of each of these individual satellites. And so if the DTM 2013 is exactly correct, then we would have a rho satellite over rho model will be equal to 1. But you can see here that there is quite a variability, and partly underlying this is a solar cycle variability. And so that means we do not know what is the absolute density of the thermosphere. We know the relative densities because we've always looked at changes in temperature and worked out what is the heat input. But the absolute density still has a very large uncertainty associated with it. So the importance of cross-calibration here, I have compared HWM 93, the Hedin wind model 93, which is the red dashed line, which is the wind speed on average throughout a 24-hour period for moderately active conditions, so KP between 2- to 4+ in solar maximum conditions, 2001 to 2003. And I've compared this is the FPI from Kiriner with the CHAMP satellite drag derived values. And what we found that the phase of the way that winds change from a westward wind to an eastward wind in the midnight area back to a westward wind is identical for CHAMP measurements, CHAMP satellite-derived winds, and FPI Doppler-shifted winds, but the magnitude is not the same. And later, Jiang et al. In 2020 found that for mid and low latitude FPIs, compared with the Gautier winds, also found a difference where the Gautier winds were larger, systematically larger than the FPI winds. So this is the importance of having independent measurements and then working out what might be wrong. We can improve observations by understanding the differences between the two. Because one of the points that I make in this paper in 2019 is that the CHAMP winds are actually larger than the plasma velocities. So Kiriner is on the outer edge of the auroral oval, and the neutral winds from CHAMP are larger than the plasma velocities within the auroral oval. So that is another cross comparison that will allow us to work out any corrections that are needed, because whenever you're making an inference, there's inevitably some parameter that we have to use from a model, or that we have to guess even sometimes. So here is an example from Elliot Dable, who's done a graph neural network flow diagram. So this is one of the things we're trying to do, where basically it's putting together data from multiple observations and balancing them and weighting them in order to create a model that will allow us to predict winds. One of the problems with Fabry-Perot observations is we can only take the observations during the hours of darkness and when there's no cloud. And for us to be able to predict what the neutral wind might be when we have gaps in our data would be a very powerful, and especially powerful if going forward into prediction tools. So what is the problem that I have about using atmospheric drag on satellites to infer thermospheric densities for models? So we have here the atmospheric drag equation, which is the underpinning drag equation of force per unit mass. And it has several components, but the components come from different areas of research. So the satellite engineers are the ones who give us the drag coefficient CD and calculate the cross-sectional area over the satellite mass region. Then we have the atmospheric physicists, and we're the ones who measure the relative speed of the atmosphere relative to the satellite. And from our global circulation models, we give the atmospheric densities. And these two communities did not really communicate with each other very much until the last 15 or so years, but they are working together more and more. But what I found very funny when I started getting involved with this is that the satellite engineers assumed that the atmospheric densities were exactly correct. They trusted us, while we, the atmospheric physicists, trusted the satellite engineers to tell us a drag coefficient that was correct. And now I've realized by working with that community that neither of us have precise measurement as much as we thought the other community had. So let's look at where is the top of the thermosphere. So here is an equation that the satellite, here's a graph that the satellite engineers are very familiar with. And it shows on the x-axis the distance from the center of the Earth in thousands of kilometers. On the y-axis, it gives you the acceleration per unit mass. And the key lines for you to observe are that it starts at the surface of the Earth at 6.4, roughly 6.4 kilometers. And we have the thermospheric boundary is between 500 to 700 kilometers. So this is a log normal axis. It's not a linear axis at the base. So this is the region where the TI-GCM, the standard model, occupies. And this top level of 700 kilometers was arbitrary. It was just chosen for convenience in the 1970s and 1980s when the major GCMs were created. But now that we're trying to look at the region where the OneWeb satellites are at 1,200 kilometers. So we're increasing the models up to this altitude so that we can help the satellite engineers work out what the satellite drag is and their precise orbit for their precise orbit prediction. Now, the main largest force on a satellite is the gravitational force of the Earth. So this is the GM value of the Earth, which is the first term in the spherical harmonic expansion of the gravitational potential of the Earth. And this is the gravitational potential of the Earth equation. And these are all the shapes that each of the Legendre polynomials give. And so you have a latitude and a longitude modes for each of these shapes. And this is the J2 zero term, J22, so on. So the higher and higher modes have smaller and smaller perturbation effects on satellite drag. Now, when we're looking at the region of the Earth's atmosphere, we can see that in this region, we have the atmospheric drag for the maximum CD. So that means a satellite that has a very large cross-sectional area to mass ratio, so it gets dragged down more quickly. And the blue line shows you the minimum atmospheric drag for one that is a very sort of bullet-shaped satellite that has a smaller cross-sectional area to mass ratio. And if we look in the region where the thermosphere is, the dominant force on drag force on the satellites is the Earth's gravitational force. And then it is atmospheric drag. And this is why atmospheric drag is so critical for the satellite industry. And so coming to the observations that we have. So the previous graph I showed, I didn't have time, is the QB50 CubeSat mission, which launched. These are real pictures, photographs taken by the astronauts on the International Space Station of the QB50 satellites. And here we had Aurelia Belkansky was an MSc project student who looked at the orbits of these satellites. So we had 28 deployed from the International Space Station and 8 were deployed from an Indian Polar Space Launch Vehicle in a polar orbit at 500 kilometers altitude. And the International Space Station was at about 400 kilometers altitude. And she was looking to see if there was a pattern. And I'm sorry this slide has got garbled and been shown. But basically she found that there was a point at which the satellites, once they got to a certain altitude, they just plummeted to Earth within 74 days. And that point she has circled here. And it changes with time. which matches the solar cycle variation, because when we looked at the International Polar Space Launch, the Space Launch Vehicle, they started to be caught by atmospheric drag at a higher altitude because it was solar maximum. And so the atmosphere had expanded into their path. And so this seemed to indicate to me that we were seeing evidence of the top of the thermosphere. At a certain altitude, the satellites then followed the same path and plummeted to Earth within about 74 days. Another example we have here is where we did a simple sort of extrapolation using Fabry-Perot interferometer data from Cachoeira Paulista in Brazil, which are the CP, the red FPI measurements of temperature, and Millstone Hill, which are the green line temperatures. So this is Millstone Hill, the solid line. Cachoeira Paulista is the solid red line. And we compared them with the MSIS analysis from that location, and we extrapolated the temperature of the, so MSIS will extrapolate to any altitude you want to. But with the FPI, we use the ideal gas law to extrapolate that temperature to altitudes of 1,450 kilometers. So beyond the 1,200 kilometer altitude where the OneWeb satellite constellation is. And what we found is the typical range of the upper boundary of the older GCMs is 400 to 700 kilometers. So within this range, we can see that MSIS and the FPIs match well. So MSIS and the FPIs continue to match well because they're all following the ideal gas law. But when we inverted the satellite accelerations with the blue line, as shown by the blue line, we found that there was a good match up to 1,050 kilometers, but then it just dropped off. So there's something funny happening here. Now, this is Laura Aguilar and Santosh Bhattarai. We're looking at the satellites by looking at the whole catalogue, the mega constellations, debris and rocket bodies, and looking and separating them to see how they were behaving, and looked at what happened during the Gannon storm, the 10th, which was between the 10th to the 13th of May, 2024. And basically, Laura plotted all the satellites and debris at the location where they were before the storm struck. And so this is set as 0. And the plots are of where they ended up after the storm, and looking at the rate of the acceleration as they are dropping from the storm. And what was very interesting is that there were different altitudes at which satellites were affected by the storm. So these are when the storm heated the thermosphere, so it expanded into the path of the satellites. So satellites in this region, which is beyond 7,000 kilometers, were unaffected by the thermosphere. So these satellites are clearly outside. The payloads and constellations are outside the thermosphere, while these are affected by the thermosphere. And the closer, lower down they are, the further they fall. But you get a separation according to what is the size of these satellites and payloads. And when you get really small debris and rocket bodies, then the top of the thermosphere is even higher up for these satellites. So that means we have to deal with the different bodies differently. But we can say that the fluid behavior extends to an altitude that is given by these vertical lines, but will depend on what is the size and shape of the body that is being investigated. And here is the final graph that I wanted to show, which is it's the same as Laura's figure, but reconfigured, and is in the paper that we've submitted to Space Weather recently. And here, all the satellites are shown their densities that have been inferred relative to a baseline density throughout the period from May the 8th to May the 15th. And they're all grayed out, but then one height region between 300 and 400 kilometers in this case is in black. And you can see the perturbation from the satellites being perturbed by the atmospheric density increasing as soon as the sudden storm commencement occurs. And it occurs in all of these, and then it starts getting messy once we get to 1200, 1300, and it's just noise above this altitude. So the issue is we're going to be using data assimilation. As we get more and more data, we're going to use data assimilation, and satellites are our best source of data assimilation. They give us our largest amount of data, the most comprehensive coverage of the globe, and so they are our best source, but we cannot rely on them to be our only source, and we have to work out where is the limit of where we will assimilate satellite drag measurements into the top of our global circulation models of the thermosphere. And we have to use all of these observations, our complementary observations. We have to keep these instruments running to validate and corroborate any observations and keep our models honest. And so I think that is the last. Yes, that is the last slide. So my reason for me giving this talk is that we must be sure that we are assimilating satellite data correctly and appropriately. To do this, we need to know what is the top of the fluid atmosphere. In other words, where is the top of the thermosphere? And that's the end of the talk. Thank you.